In science, we've got to deal with numbers a little differently. In fact, we probably don't even refer to them as numbers. We would refer to them mostly as measurements. And so because we refer to them as measurements, the instrument that we use to take the measurement only gives us a certain amount of information. Let me do kind of a compare and contrast. In math class, if you were looking at a number like 125, and you were asked the question, well, what comes after the 5? Well, in math class, the answer would be, well, a 0 does. And then, well, what comes after that? In math class, it would be another 0, and then so on and so on. It would all be zeros. But in science class, when you take a measurement, and the measurement is, let's say, 125 meters, when we ask what comes after the 5, the real question is we don't know. Because we're trusting that the measurement as written, 125, was measured with something that only gave us information down to the ones place. And so we would also say that that last digit was estimated. And if we're estimating what's in the ones place, then it's 10 times harder to estimate what's in the tenths place. So if we look at the thermometer here to the right, and we look at the measurement here, let's see, every line, big line here looks like 5 degrees, so we've got 100 degrees, 105 degrees, 110 degrees Fahrenheit, and so then each line is 1 degree. So we know by looking at this that this is between 103 and 104 degrees Fahrenheit. But we can estimate, right? We can clearly see what is that it's not on the 103 and that it's not on the 104. We know that the measurement is less than 104 but greater than 105. And so we might estimate this to be 103.5 degrees Fahrenheit. And since we estimated the tenths place, we can't even think about what's in the hundredths place. We don't know. Here's another example, measuring a quarter here. Each line on this ruler represents a millimeter. And so we've got the lines drawn here. Whoops, we've got lines drawn here for each of those. And it looks like, well, this is between 24 and 25 millimeters. And so if we all measured this quarter with the same device, we would definitely agree on the 2 and the 4, right? We're pretty certain about what's in the tens place and what's in the ones place. And we can see that it's between 24 and 25, and so we have to estimate what's in the tenths place. Now, if I measured this and estimated that digit, and you measured this and estimated that digit, we might not come up with the same thing. One of us might say 24.6, the other might say 24.7. And that is okay within the tolerances of this device. All right, so anytime you take a measurement, there's always recorded what's certain, and then you have to estimate one more digit. All right, you read what you can off of the device, and then you estimate one more digit. Second. In this measurement, all of those digits are significant. So we would say here that there are 3 significant figures. Because we were certain about the 2 and the 4, and we estimated the 6. Now, we're not always going to have measurements taken. So when we see a measurement or a number written down, in a textbook or on a problem, or maybe it's a measurement that someone else took, how do we know? We call them, how do we know what the significant figures are? Well, if we go back here for a quick. And so anytime we're dealing with a measurement, any non-zero digits, they're easy. Anytime there's a non-zero digit in a number or in a measurement, that non-zero digit is significant. The hard part comes in dealing with the zeros. Zeros are sometimes significant and sometimes they're not. It kind of all depends on where they occur in the measurement. So, for example, number 2 here says interior zeros, or zeros between two numbers, are significant. So in this example here, the 0, this 0 here is between the 4 and the 2, so that 0 is actually part of the measurement. There's a 0 between the 2 and the 8. That is also significant. And then in this other number, 50.1, the 0 is between the 5 and the 1, and so that is also a significant digit. Right? It's actually part of the measurement. Sometimes zeros just hold a place. They tell us how big or how small a number the number is, and we'll get to that in a minute. But here at rule number 3, we're looking at trailing zeros that are after the decimal point. All right, trailing zeros that are after the decimal point. Are they significant or not? And we're going to say that they are significant. We look at this 0 here at the end of 5.10, and if it's not significant, why would we include it in the first place? Why not just write 5.1? Or in this other measurement, why not just write 3? Is there a difference? Yes, there is. So if I compare 5.1 and 5.10, in this first measurement, the 1 is estimated. But in 5.10, the 0 is the estimated digit. So the 5.10 is a more precise measurement because it gives more detail to the measurement. It gives detail down to the hundredth of whatever unit we're talking about here. Whereas 5.1 only gives us information down to the 10th of the unit. Rule number 4, also dealing with zeros, also dealing with trailing zeros, but this time they are zeros that fall before a decimal. Now we have a couple of scenarios here. Zeros that fall before a decimal point are significant. So in the case of 50.00, all 3 of those zeros are significant. The 2 to the right of the 0, the 2 to the right of the decimal point are significant. Go back to rule 3 for that. And the 0 to the left of the decimal is significant also. This is kind of like the sandwiched zeros or interior zeros. Right? If these zeros to the right of the decimal are significant, then this 0 that's kind of sandwiched in between significant digits must also be significant. Same thing here. These zeros in the 1700.24, they're sandwiched in between the 7 and the 2. And since the 7 and the 2 are both significant, so are those zeros. Now, rule 6 is when it gets a little unclear, or as they say here, ambiguous. That's just a way of saying unclear. So let me give you a couple of examples here, and I'll tell you how we're going to handle these ambiguous situations. If there is a measurement 350 centimeters, and this measurement 350 with a decimal point centimeters, I'm going to say that this is 2 sig figs. Sig figs is my abbreviation for significant figures. And that this one represents 3 significant figures. Okay, I am going to make the distinction, even though our book doesn't necessarily do this, that when a decimal point is included, excuse me, I've messed this one up a little bit. Let me make this 350, sorry. All right, the 350 with this decimal point, that decimal point means that this 0 is estimated. In this top measurement, the tens place is estimated. So what's the point of that 0? Well, that 0 is simply a placeholder. If we were to write this in scientific notation, we would write it this way: 3.5 times 10 to the 2. Right, and that 0 that's holding a place there gets wrapped up, right? This 0 that's holding a place gets wrapped up into the exponent of the scientific notation. Now, on this second measurement, 350 with a decimal point, that would be 3.50 times 10 to the 2. And of course, I should put my units on here. All right, so scientific notation clears up the ambiguity. Right, it's really incumbent upon the measurer, or it's the responsibility of the person measuring, to clearly state how many significant figures there are in the measurement, to clearly indicate what the estimated digit is and what it is not. And so the best way to do that sometimes, especially if there ends up being a 0 to the left of the decimal, the best way to do that is with scientific notation. But we will also say that if there is a decimal point included there, then that 0 also is a significant digit. So a quick set of sample problems here dealing with significant figures. All right, we look at A, and that has 2 significant figures. These zeros, leading zeros to the right of the decimal, are simply placeholders. So again, if we write this in scientific notation, 3.5 times 10 to the minus 3, right, those zeros are just showing us, right, the zeros are just showing us how small the number is. Right, they get wrapped up in the exponent here, 10 to the minus 3. So only the 3 and the 5 are significant. For letter B, 1.080. That has 4 significant figures. Right, this 0 is an interior 0, or it's sandwiched in between the 1 and the 8. And then this trailing zeros to the right of the decimal, are significant. And then C, 4 significant figures. All non-zero digits are significant. D, any digit in scientific notation, or all digits in scientific notation, are significant. So that should be 3. I'm going to skip over E for a minute. I'll come back to it. F, 100.00. Well, let's start with the 0.00 numbers. We know that zeros to the right of the decimal are significant. So then what about these guys? Well, if these are significant and the 1 is significant, then we have zeros sandwiched between non-significant digits, so they are also significant. So that's 5 significant figures. And then how about G? Well, G is unclear. But our rule that we applied said if there's no decimal, then the zeros are just placeholders. So then our estimated digit is in the 100,000s place. So there's 1 significant figure, right? And the rest of those zeros are just showing us how large this number is. 1 times 10 to the 5th power. And then back to E. There are some, we'll call them measurements or numbers, that are exact. And so exact things are like 1 meter equals 100 centimeters. Right? Exactly 1 meter equals exactly 100 centimeters. It's kind of by definition. Another way to write this might be 1 with a repeating 0, right? 1.0 repeating meters is equal to 100.0 repeating centimeters, right? Exactly 1 meter is exactly 100 centimeters. So 1 dozen is exactly 12. So in essence, that has an infinite amount of significant figures, or unlimited significant figures. It's not just one, or it's not just two, right? It's 1.0 repeating dozen is equal to 12.0 repeating of whatever it is that we're counting, right? 1 dozen is exactly 12. Now, there are some cases where a relationship like that is not going to be an exact relationship. Think about this. 1 inch is equal to 2.54 centimeters. I don't look at that as an exact. I would say that this is not exact. In fact, I think this is better written this way. 1.00 inches is equal to 2.54 centimeters. And that would be 3 significant figures there. Right, the 100 and the 254. You kind of want to be consistent there to clearly show 3. It would be weird to say, if we looked at this one up here, it would be weird to say 1 significant figure on the left and 3 on the right. That's inconsistent. So in a non-exact relationship like this, you've got the same number of significant figures on each side. So in the next lesson, we'll look at how to determine or how significant figures impact calculations. So I hope this one was helpful. I hope that helps you get through the homework.